All right, let's talk about the rules of chance. In this explainer, we're going to demystify the core rules that actually govern probability. And just so you know, everything we're going to be diving into today comes straight from this fantastic textbook, The Essentials of Statistics by Mario Triola. So we've got a really solid foundation for everything we're about to cover. So here's our game plan. We're going to start with the absolute basics, the building blocks. Then we'll get into the two heavy hitters, the or rule and the and rule. And finally, we'll see how this stuff actually matters in the real world. All right, so first things first. Before we can get to the fancy rules, we have to define what we're even talking about when we start combining different events together. You're going to hear this term a lot, compound event. And it's not as scary as it sounds. All it means is any situation that combines two or more simple events. So instead of just flipping one coin, maybe we're flipping two coins. That's a compound event. And getting this idea down is really the key to everything else we're going to learn. Okay, with that foundation laid, let's get into our first big rule. This is the one we use when we want to figure out the probability of event A times or event B happening. And listen, if you remember one thing from this section, make it this. When you see the word or in a probability problem, your brain should immediately think addition. It's the most important mental shortcut. Or means we're going to be adding some probabilities together. So here's what the actual formula looks like. We take the probability of A, we add the probability of B, and then, you see that last part? We subtract the probability of A times and B happening together. Now, why on earth are we subtracting something? Well, it's actually pretty clever. It's to make sure we don't accidentally double count any outcomes that might be in both groups. And to really get why we sometimes have to subtract that overlap, we need to talk about something called disjoint events. You might also hear them called mutually exclusive. It just means two events that absolutely cannot happen at the same time. There's zero overlap. And this slide, this is a perfect illustration. Look at the left, selecting a male or a female for a trial. Those are disjoint events, right? A person can't be both. But now look at the right, selecting a statistics student or a female. Well, can you be both of those things at the same time? Absolutely. So those events are not disjoint, and that's the kind of overlap our formula has to account for. Now, speaking of addition, there's a really cool shortcut that stems from it. It's called the rule of complementary events, and it's based on a really simple truth. Something either happens or it doesn't. There's no third option. So the chances of both have to add up to 1. Or 100%. And this gives us a super fast way to figure out the odds of something not happening. So let's put it to the test with a real-world example. We know that the probability of a US household having a smartphone is 0.87. So what's the probability that a household does not have one? Boom. Simple as that. We just take 1, subtract the probability of having a phone, and we get our answer, 0.13. See how easy that is? It's a super useful trick to have in your back pocket. All right, we've nailed the OR rule. So now let's switch gears and talk about our second major rule, which is what we use when we want to find the probability of one event happening and then a second event happening right after it. And you guessed it, just like we had a shortcut for OR, we've got one for AND. If OR means add, then AND means multiply. It's that simple. Anytime you see AND connecting two events in a sequence, you should be thinking multiplication. Okay, let's look at the official formula. You'll see this new piece of notation here, that little P of B comma A part. What on earth is that? Well, all it means is the probability of B given that A has already happened. And that's absolutely crucial, because sometimes the first thing that happens can completely change the odds for the second thing. And that whole idea of one event affecting another brings us to this really important concept, the difference between independent and dependent events. Independent is like flipping a coin twice. The first flip has no effect on the second. But dependent is like drawing two cards from a deck without putting the first one back. The first card you draw changes what's left in the deck, right? Okay, let's make this real. Check out this table. Imagine we've got 50 drug test results from a group of people who use drugs. 45 of the results came back positive, 5 came back negative. We're going to randomly pick 2 people from this group. So for our first scenario, let's imagine the events are independent. How do we do that? We sample with replacement. That just means we pick someone, check their result, and then, this is the key part, we put them back into the group before we pick again. So how does the math work out? Well, the chance of that first pick being positive is 45 out of 50, right? And because we put them back, the total is still 50 for the second pick. So the chance of the second pick being negative is 5 out of 50. We just multiply those two together, and there's our answer. Okay, that was with replacement. But what if we change one little thing? What if we don't put that first person back? Now the events are dependent. And this is where it gets interesting. Look closely at that second number. The first part's the same, 45 out of 50. But because we didn't replace that person, there are now only 49 people left in the pool. So the probability for the second event changes. It's now 5 out of 49. It's a small change in the numbers, but it definitely impacts the final answer. Okay, so we've got these rules, right? The or rule, the and rule. But what's the point? Well, this is where it gets really cool, because we can use this stuff to understand risk, reliability, and how we build systems to keep us safe. Now, speaking of real-world stuff, statisticians have this handy little rule of thumb. It's called the 5% guideline. Basically, it says that if you're taking a tiny, tiny sample from a huge population, like less than 5%, you can kind of cheat. You can treat your selections as independent, even if they're technically dependent. It just simplifies the math without really messing up the result. All right, let's look at an awesome practical example. Your computer's hard drive. Let's say we know that a certain model has a failure rate of 2.89% in a given year. So what are the chances it'll actually work just fine for the whole year? And hey, we know how to solve this. It's our old friend, the rule of complementary events. We just take 1 or 100% and subtract that probability of failure. And that tells us we've got a 97.1% chance that the drive will be just fine. Okay, 97.1% is pretty good. But what if pretty good isn't good enough? What if this is mission-critical data we're talking about? What happens if we put a second hard drive in the computer as a backup? Now, figuring this out is a brilliant little puzzle. Think about it. What's the only way for you to lose all your data? The only way is if both drives fail. So we can calculate the probability of that one bad outcome. That's an and problem, right? Drive 1 fails and drive 2 fails. So we multiply their failure rates. Then we just use our complement rule again. We take 1 minus the probability of that terrible thing happening. And just look at what happens to our reliability. It skyrockets from 97.1% all the way up to 99.9%. That is a massive, massive improvement in safety, all from adding just one backup component. And this idea, this principle of redundancy, is one of the most powerful real-world applications of the multiplication rule. You see it everywhere, from complex engineering to, believe it or not, our own biology. So it really makes you think, doesn't it? Now that you know the rules behind it all, where else do you see this idea of redundancy protecting you? Think about it. The 2 kidneys in your body, multiple engines on an airplane, backup power systems at a hospital. These simple rules of chance are literally at work all around us, keeping us safe every single day.